So, welcome to the remaining part of the lecture on the non-radiating dielectric guide. So, today we are going to finish the explicit field expressions for the remaining modes of the NRD, as well as discuss the characteristic equation of the NRD from which the cutoff frequencies of all the modes can be obtained. So, the last time we had discussed the explicit field expressions for the LSM even mode. We are going to write down the explicit field expressions for the LSM odd mode and thereafter the LSE even mode and the LSE odd mode. Okay. Not a very difficult exercise, but just for reference sake. You should verify yourself as you see these expressions. So, for the LSM odd mode, we write in the dielectric region, which is mod x less than or equal to V by 2, Ex is A d 0 k 0 square epsilon r minus q m o square by j omega epsilon naught epsilon r sin q m o x sin n pi y by b e to the power minus j k z naught z. As before, k z naught O stands for the odd mode. E y is given by A d 0 q m o n pi by j omega a epsilon naught epsilon r cos q m o x cos n pi y by a. Sorry, there is a small error. This should be a instead of b. So, sin n pi y by a. So, similarly cos n pi y by a e to the power minus j k z naught e to the power minus j k z naught z. So, that is equal to minus a a naught. So, this is the expression for x lesser than or equal to minus b by 2. So, minus a a naught p m o square plus k 0 square divided by j omega epsilon naught exponential minus p m naught mod x minus b by 2 sin n pi y by a e to the power minus j k z o z for x lesser than or equal to minus for x lesser than or equal to minus b by 2. Okay. Similarly, E y is minus a naught n pi p m o by j omega epsilon j omega a epsilon naught exponential minus p m o mod x minus b by 2 cos n pi y by a e to the power minus j k z o z. E z is a a o k z o p m o by omega epsilon naught exponential minus p m o mod x minus b by 2 sin n pi y by a e to the power minus j k z naught e to the power minus j k z o z. H x is 0, H y is minus a a o j k z o exponential minus p m o mod x minus b by 2 sin n pi y by a e to the power minus j k z o z for x greater than or equal to b by 2, and that is equal to a o j k z o exponential minus p m o mod x minus b by 2 sin n pi y by a e to the power minus j k z o z for x less than or equal to minus b by 2. H z is minus AAO times n pi by A exponential minus PMO mod x minus b by 2 cos n pi y by A e to the power minus j k z o z for x greater than or equal to b by 2, and that is equal to AAO n pi by A exponential minus PMO mod x minus b by 2 cos n pi y by A e to the power minus j k z o z for x lesser than or equal to minus b by 2. So, now equating the tangential magnetic fields at the air dielectric interface, we will obtain the equation which we obtained similar to the previous case for the LSM even mode. So, equating the tangential magnetic fields at the air dielectric interface we obtain the relationship between ADO and AAO. So, ADO sin q MOB by 2 is equal to AAO. So, now we do the same exercise for the LSE even mode. Let us write down the explicit field equations in the dielectric and air regions. So, for the LSE even mode, in the dielectric region, which is mod x less than or equal to b by 2, we have E x equal to 0, E y as j k z e prime b d e cos q m e prime x cos n pi y by a to the power minus j k z e prime z. then E z will be minus B d E n pi by a cos q m E prime x sin n pi y by a e to the power minus j k z E prime z. H x is B d E k naught square epsilon r minus q m E prime square by j omega mu cos q m E prime x cos n pi y by a e to the power minus j k z E prime z. H y is given by B d E q m E prime n pi by j omega a mu sin q m E prime x sin n pi y by a e to the power minus j k z E prime z. H z is B d E k z E prime q m E prime by omega mu sin q m E prime x cos n pi y by a e to the power minus j k z E prime z. Now, in their region which is mod x greater than or equal to b by 2, E x is 0, E y is j k z E prime b a e exponential minus p m E prime mod x minus b by 2 cos n pi y by a e to the power minus j k z E prime z. E z is minus b a e n pi by a exponential minus p m e prime mod x minus b by 2 sin n pi y by a e to the power minus j k z e prime z. H x is given by B A E P m e prime square plus k naught square by j omega mu exponential minus p m e prime mod x minus b by 2 cos of n pi y by a e to the power minus j k z e prime z. H y is B A E P m e prime n pi by j omega a mu j omega a mu exponential minus p m e prime mod x minus b by 2 sin n pi y by a e power minus j k z e prime z, that is for x greater than or equal to b by 2, and that is equal to minus b a e p m e prime n pi by j omega a mu exponential minus p m e prime mod x minus b by 2 sin n pi y by a e power minus j k z e prime z, that is for x less than or equal to minus b by 2. And H z is given by B A E k z e prime p m e prime by omega mu exponential minus p m e prime mod x minus b by 2 cos n pi y by a e power minus j k z e prime z, that is for x greater than or equal to b by 2, and that is equal to minus b a e k z e prime p m e prime by omega mu exponential minus p m e prime mod x minus b by 2 cos n pi y by a e power minus j k z e prime z for x lesser than or equal to minus b by 2. So, in this case we equate the tangential electric fields at the air dielectric interface in order to find the relationship between the coefficients in the dielectric region and the air region. So, equating the tangential electric fields at the air dielectric interface we obtain BDE cos QME prime B by 2 equal to BAE. Okay, so, this completes the field description for the LSE even mode. Let us stop here. We will continue with the LSE odd mode in the next lecture. Thank you.